Good afternoon, everyone. I hope you are doing all right and ready to learn some physics. So, today we're going to be building up on what we learned last class. So, we learned that when a charge is moving in a magnetic field, something like this, then it experiences force. And the value of that force is given by QV B sine of angle between B and B. And the direction is given by a right-hand rule. So here is one proof, how nature, basically how this thing happening or how the force is acting on moving charges when they enter the Earth's magnetic field is displayed in both northern and southern pole or hemisphere of the Earth near the poles. Okay, if you are far from pole, it's hard to see, but this year we had display, these lights visible from here from Colorado as well. That's very rare, but sometimes it happens. So last class we did a problem where these protons were entering Earth's magnetic field, and we calculated how much force they experience and what's the direction of force that's acting, right? So that's what we did. So basically, that's what happens. These charged particles are entering to the Earth's magnetic field, and the charged particle originates from the sun. So sun is burning hydrogens and emitting a lot of energy. So there is a lot of thing going on, and it has a magnetic field as well, a really large magnetic field compared to the Earth. So in the process of that burning, just like when a wood is burning, coal is burning, there are sometimes, something skip out from there, right? It ejects some sort of mass. So same thing is true here as well. So from the sun, what happens? Mass gets ejected, and those masses comes as elementary particles like protons, electron, or other some elementary particles. So when they enter Earth's magnetic field, they experience force. Okay? And when they enter, they may not always enter perpendicular to the magnetic field. They may enter at any angle. So what happens is we can think of that velocity at a particular angle as the perpendicular component and parallel component to the field. So the perpendicular velocity makes this particle go in circle. And the parallel component of the field that basically pushing this particle in the direction of field. So because of that, what happens is that the charges gets spiraled towards the pole, towards the stronger magnetic field. So when they enter to the Earth atmosphere, they hit the atmospheric particle, right? For example, oxygen, nitrogen, and carbon dioxide gases that exist in our atmosphere. So when they hit those, what happens? Those gas they also have electrons. So when this fast moving particle comes and interacts with them, some of these particles get ejected from the orbit of those elements, gases, okay? And the electrons jumps up and comes down. In that process, they emit the light, okay? And light color basically depends on the wavelength of light or frequency of light. We'll talk more about light in the coming chapters, but what happens is this process of the electron going higher and then eventually coming back and combining with one of those again, so that when this process continues, they release light, just like the electrons in the light bulb. They are jumping around and then releasing some light. So similarly, it's releasing that light, and the color depends on how energetic the ejected electron is. And the energy of the ejected electron is going to depend on, like what molecules or the atoms they are ejected from. And that eventually depends on also on the solar energy of the solar particle. Okay, more energetic particle that's arriving, they can penetrate through and eject more energetic. So more energetic they are, that means they are kind of more bluish in color and not that energetic. That's the red. So in the spectrum, it goes from blue or even purple all the way to the red. Red has the longest wavelength. Okay. So, and longest wavelength means, let's say, the frequency is inversely related to wavelength. And so less frequency. So that's how these color display of light we can see. So when we actually look at from the Earth's surface, we don't see this whole nice thing, right? So this picture is taken from space, as you can figure. But when you are here on the Earth, and you are looking at just part of it, okay? Part of this. That's what you are seeing when you are looking from the Earth, just a small portion of that tall display of light. Okay, so they go hundreds of kilometers high because atmosphere starts from there. Okay, so that's aurora borealis, and of course, same thing also happens on the southern hemisphere. I think that's called aurora australis because it's on the Australia side. Okay, so that is the deflection of the charged particle in Earth's magnetic field. So now let's do similar experiment here on the Earth. So let's pass the charges. Oh, I did not animate them. Okay, so let's pass the charges. So when we show current, that means it's the charges that's flowing, right? So it's going in the conductor. So there is a conductor. So that means it has both positive and negative charge in the conductor. And you are now injecting with the extra charge as well. So now you put that conductor in a magnetic field. So based on this cross, we can tell the magnetic field is going into the page or the screen. Okay, so that's what happening here. So magnetic field is entering into the screen in this case. So now that means the current flowing this way means, let's say there is a positive charge Q that's moving this way, right? Current flowing this one means the positive charge is flowing this way. So let's look at the forces acting on this using right-hand rule. Okay, so when we apply right-hand rule, by, let's say, since current is flowing this way, we can say, okay, V, or the velocity of the charges, are to the right. And remember, field is going into the page, so you need to free up your right hand, right? Stretch your thumb, and then orient it to the right, like that. And is that right for you or not? But make sure you go towards the right because the charge is moving to the right. And remember, this has to be right hand, okay, not the left hand. So you do that and see how I'm not putting my palm up, rather I'm putting my palm down so that I can crawl it down. Why? Because field is going into the page. When that happens, the thumb kind of points up in the screen. So that's why when the charges are moving, at the same time, they are also drifting up, positive charge. And for the negative charges, of course, it's going to be opposite. So negative charges pile up over here in the conductor. So now there is sudden development of positive and negative charge, just like we have in a capacitor plate, for example, right? So when we have that, it's like a capacitor plate, or let's say battery. Oh, okay, so positive charges here, negative charges. So that means we say, okay, there is potential difference, or there is potential difference whenever there is positive and negative charges separated. So that's what happening here. So there is this potential difference. So this developed potential difference is called the Hall voltage. Okay. So we can also think of this as an electric field going from positive charge to the negative charge, or we can talk in terms of potential difference, or we can use both depending on what we want. Okay. So here what happens is, like, the separation of charge continues until, so that means a charge now experience both kind of force. There is force due to magnetic field, and then there is force due to electric field, right? So when they balance, then the separation process stops. So they are now just drifting, and there is pile up uh, charges, and there is potential difference, or there is field. So it's so the field, or this potential difference, I should say field, since I'm going to talk about direction here. So the field is along the surface of the conductor, the electric field, but the magnetic field we are applying is perpendicular to the conductor. So that means E and B, they are perpendicular to each other. So that's why the crossed field, right? So if, let's say, one is going this way, another one is going that way. So let's say that's B, that's E, then angle between them is 90°. So we call that crossed field. And this developed potential is also called Hall voltage. Probably you can guess this effect was first discovered by some scientist named Hall, right? So here, when these forces are in equilibrium, we can say, okay, force due to electric field is Q times E, and force due to magnetic field is QVB. Here sine theta is 1 because the angle between B is going that way and B is going into the page. So the angle between them is 90°. So that's why sine theta becomes 1. So I'm writing like that, okay? So when these charges are in equilibrium, means the forces are balanced. One force is balancing another one. So that's why they are equal. So now we can cancel the charge. And this gives us relationship between this developed electric field and applied magnetic field and the speed. Okay. We can also tell, okay, with what speed. So when they are in equilibrium, when they are fully separated, we can use this equation and find the speed of the charge, how fast they are moving now, drifting in the conductor. Okay, so if we, E is supposed to be B, not V. V I'm calculating. So we can calculate like that. But here we are interested in this Hall voltage, or the potential difference. And potential difference and the electric field, they are related. We define electric field as delta V over delta X. And to indicate direction, we put the negative sign. So here, direction is already indicated by the arrows. So that means we can just say this. So this is delta V, and delta X means this width of this conductor, right? So if this is wire, something like this, so one side they're going to be positive charge, another side is going to be negative charge. So there is the separation distance between them, which is equal to the diameter of this wire. So we can say, okay, that displacement is equal to diameter of the wire, or whatever distance that is. And that I am indicating by writing D over here, and that's what I am doing here, okay? So that means I can replace this E by that delta V over D, and that can be solved for delta V, and this delta V is called Hall voltage, and this is product of velocity, strength of the magnetic field, and the separation distance between the charges, which turns out to be equal to the diameter or width of the conductor. Okay. And you can actually measure this potential difference using a voltmeter, for example. Okay. So now our body has a blood, and blood is made up of ions, positive and negative charges, right? So, I mean, blood has a lot of things, but there are some, for example, if you, I don't know if you have ever tested blood. I'm not saying you are a vampire or something like that, but it tastes salty. So salt means sodium chloride, okay? So sodium chloride, when you put salt in water, it basically gets into sodium and there are is chloride. So our blood has all these different kind of minerals that basically transporting to different part of our body that gets absorbed, right? So it has these kind of ions and the blood is moving. So in physics 2, not physics 2, physics 1, in fluid dynamics, we talked about, flow of blood in arteries and vein, and there was a question related to that on the worksheet as well. Okay. So over there in that example, I said, okay, there was a plaque, right? So the plaque can build up. And what happens? So when we have a arteries or vein, and if there is a plaque, something like this, let's say, so in this region, the area becomes smaller. In this region, area becomes larger. So where area is smaller, B becomes larger. So speed of the blood changes when there is a plaque. Okay. So now let's suppose if you are having problem in your hand, leg, or part of body, and if doctor thinks, okay, there may be a plaque, what they can do is they can like let's say confirm that by putting magnetic field. Uh, you know, eh, let's say insert your hand and supply the magnetic field, and then it's going to develop potential difference, just like in case of Hall voltage. Okay. And you can measure that potential difference and find the speed and how fast and how slow they are moving. And based on that, you can calculate, okay, how much the plaque is in your body, okay, or in your arteries or vein. So for example, you apply magnetic field. Let's suppose this is your arteries or vein where the blood is flowing, which contains the ions, which are charged, positively or negatively charged, and you apply magnetic field, what happens? They get separated like that. And of course, they are also moving. So that's what develops the electric field, or there is that potential difference. Now you can measure that potential difference. And usually we can tell, okay, what's the diameter of arteries or vein of a typical person, right? So we can use that D. You measure the potential difference, and from there you can calculate V. Of course, since you are applying magnetic field, you know what the magnetic field is. So your device gonna do the math right there, right? It has that little calculator and gonna display the speed. Okay, but that's how this, this is the physics behind the design of that kind of device. Okay. So for example, here is this problem. It says has an inside diameter of 4 millimeter. Millimeter. So looks like there is a message that says you started attendance on iClicker. I don't take the attendance. I do the poll. Okay. And we are almost there. Yes, I haven't. Looks like you started clicker or class. I started clicker but did not start. Okay. Thank you for heads up. So D is 4.00 millimeter. And in this case, magnetic field is that many Tesla. And all EMF measured was that much. So 30 microvolt. Oof. So that is delta V, which is 30 microvolt means 10 to the power negative 6 volt. Milli has 10 to the power negative 3. Let me convert that into millimeter. So to the meter and potential difference in volt and so on. So those are the things that's known. And now it's asking what is the average velocity. So basically that velocity in that formula, right? So we can use this formula. So delta V is V B D. So V is delta V. Oh, I have to be careful about uppercase V versus lowercase v. They are both here. Uppercase V is potential difference. Lowercase v is speed or velocity, value of velocity. So that means I can do this B and D. And then now delta V 30.0 times 10 to the power negative 6. B is 0.100. And then D is 4.0 times 10 to the power negative 3. It looks like this is going to give us around 300 times 4 is 1200 times this goes over there. So it makes this 10 to the power negative 3 meter per second. So 3 zeros, 1, 2, 3. Hey, 1.2 meter per second. Looks like that's moving really fast. I don't know if these numbers are reasonable, but looks like that's the speed of blood in arteries. Okay. So that's how you can measure this speed. Okay. In speed of blood flow in our body. I think I did not do it correctly. I should have divided this by 4, rather I multiplied, so that's why the number was big. So 300 needs to be divided by 4, not multiplied. Looks like it's going to be something. Oh, divide, not multiply. Why am I writing multiply? Okay. So it looks like it's going to be 0.7 meters per second. That seems more reasonable. Okay, so that's a blood flow meter. So now we said, okay, basically source of magnetic field is moving charge. And moving charge experience force in magnetic field makes sense because moving charge itself is like a magnet, tiny magnet, and the magnetic field is a magnet. So they are like saying two magnets, okay? So that's why moving charges experience force in magnetic field, just like one magnet and another magnet experience force. So charges, when they move, they act like a tiny magnet. That's the origin of the magnetic field. That's what we learn, okay? So that's why the charges experience force in a magnetic field. And here is one such example. For example, when we say current, it is basically flow of charges. We know that. So for example, let's say you pass current through a wire and you put this compass. What happens? Compass tries to align themselves with the direction of magnetic field. So here on the earth, the compass points to the north because we have earth's magnetic field, right? So that's why it's pointing north-south, because earth's magnetic field goes north-south. So here, why these compass are pointing in kind of in a circle, let's say, if we connect those, all of those, they are forming kind of circular pattern. And to confirm that, we can also do experiment something like this. So there is this thick wire passing, okay, double wire. And then there are these tiny iron dust. Okay, so iron, they are magnetic, paramagnetic material. So they get attracted due to the magnetic field. So you see here, they kind of circle around, see? They circle around, okay? So this magnetic field due to current in a wire is given by, let's say, so to find the direction, we can use right-hand rule. Remember, we're going to be using right-hand rule uh, several different ways. So this time what we are doing, we are grabbing the wire. So let's suppose this is wire, and let's say current is going up. So you want to put your thumb lining up with the current and then grab that wire. So whatever direction your uh, fingers are curling, that's the direction of magnetic field developed by the current in the wire. So that's why you see here. So there is the direction of current, and that's where we pointed the thumb. So when you do that, it's going to circle the wire like that. So that means these are the magnetic field. Of course, they're going to be in full circle. Here to make room for the hand is done here. So I found this picture in Wikimedia. I did not make it. Okay. So that's the direction we can find. And our finger kind of circulates, right? So it's nice representation over there. So is it going to be circulating this way or going to be circulating that way? It's going to depend on whether current is going up or current is going down. Okay, so that's what happens. So now to find the magnitude, so that's what the Ampere's law gives us. So that equation also, as we expect, depends on the current and how far the point is. So this equation is very similar to magnetic field at the center of wire due to a current loop. So if this is magnetic field and if current is going, we said, okay, that field is to R. Okay, that's what we said. So they are very similar. So here this is pi over there. Okay, so this is the magnetic field inside the loop, current loop, but this is the magnetic field due to a straight wire, and the magnetic field lines are looping here. Okay, over here magnetic field lines were going kind of straight, and current was looping. So there is slight difference. So they look very similar, but there is difference. So don't get confused, okay? So now it's your turn. So B is mu naught I over 2 pi R. So here you saw sometimes current may be, flowing through the two wires, right? And if they are going down, both going down, or bias is both coming up, or one may be going down, another may be coming up, something like that, may happen. So over here it says, okay, it's going like that, but there is a little bit, folding on the wire in some places. So that's what's happening here. So you are asked to find this, right? So I'm opening the pool and I am giving you a minute and 30 seconds to pull on this now. Maybe 2 minutes for this. Take your time. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got. So mostly B. So it's asking for biggest to smallest. Okay. How do I do it? So here I sketched. That now looks like a funny face. So I sketched that, the direction of magnetic field. So if you were to grab this wire with the thumb pointing in that direction, your finger gonna come from this side. So it's like magnetic field coming out, right? And over here, magnetic field going in, right? So that's what happens. So there's gonna be some magnetic field. Over here, if we do the same thing, it's gonna give the same, right? So they're gonna be dot, dot, cross, cross. But if we do the same thing over here, what's gonna happen? Since it's going in the opposite direction, now what's gonna happen? So when I grab the wire with my, let's say, hand with that thing pointing, so what happens here? current is in opposite direction. So the magnetic field due to this one going to be circulating exactly opposite to that. So there going to be some cancellation. Dot dot over there. So when I grab that, what's going to happen? From this side is coming out. So basically, they are coming from this side, they are coming from that side, and looks like they're going to be cancellation because they are in opposite direction. Okay, some cancellation, or maybe all of it going to be canceled. Now over here, using the same idea, since the current is going in the same direction, so that means they're going to be circulating in the same direction, so that means field going to add up. So that means it's going to be largest. And since there is cancellation happening, so that's going to be the smallest. So one going to be in between, looks like. Okay. And so that means 3, 1, 2. Do we have that here? Oh, looks like we don't have any of those. So that means we have to go with this. Yeah, the B was close, but it's supposed to be something like that, folks. So it's like saying, okay, net current here is like a 0 because it's going one way versus the other way. But current itself is not 0, but the field due to them basically tends to cancel. Okay, so yes, folks. And looks like we have a number from the last problem. And that's not 0.7, but 0.07. Okay, thank you. Okay, anything you like to add or ask here, folks?
Can you hear me?
Yeah.
Okay. Um, could you just briefly explain one more time? Like, I get why one and two cancel, but why is three the largest exactly? I don't know. I'm kind of just confused.
1 and 2 does not cancel. Only 2 cancels. I mean, this point here, the current is going this way versus that way. Current is going in opposite direction means, let's say if magnetic field of these two, right? So one current going this way means, let's say if it's going up, so this magnetic field going to be circulating this way. But this current is going down means the magnetic field due to this going to be circulating exactly opposite. So this magnetic field being vector, what happens? They cancel when they are in opposite direction. So at point 2, they cancel. But in point 3, what happens? Both of these currents are in the same direction. See, they are flowing in the same direction. Both of them going to the right. Means they're going to add up. So that's why it's going to have the largest value. And since they are canceling here, it's going to have the smallest or even 0 value there. And this one has its own in between. Okay. So it's going to be 3, 1, and then 2 in terms of biggest to smallest. Okay. That is that helpful? Is that enough? Hey, I suppose so. Let's move on. So we learned that charges experience force, and last class we had this demo of the electron beam moving, and then this person brought magnet and the beam was deflected, right? in a direction perpendicular to the magnetic field. So now current carrying wire is basically the wires have charge moving. So the current have just moving charges. So the exactly is the same thing, right? And here is another demo done by another teacher. Okay. So let's watch this video. So I have here a large magnet, south pole, north pole. So the field is pointing up. And then I have a big, well, copper tube, which is connected to the wires here and there. When I connect these here, electricity will flow through this guy, through the red, through the copper tube, and then up through ground, and then back home. So we'll have electricity flowing this way, magnetic field pointing up. Oh. So current flowing this way in the wire. Okay, I'm drawing on the screen. And magnetic field is this way. So which way we expect the force to be? So this is B and this is I. Can you use your right hand rule? Think about current as the velocity of the positive charges, right? So you start by moving, lining up these fingers in the direction of the flow of current, and then you crawl them to the direction of magnetic field. Okay, so let me make so you guys figure out that, and I'll make a clicker question. Direction of force is what? A, let's say, towards south pole of the magnet, right? South pole is here. So that means up. Another way to say that is up. Or B, towards south pole and towards north pole. And C, let's say, towards magnet means this way, folks. See here, the magnet, this magnet, Warsaw magnet. So this way, okay, I'm saying towards magnet. And D is, let's say, away from magnet. So what do you think? Right? So now I'm opening the poll and you have a minute. So this I is like a V, okay, for a charge. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. So mostly C. What is C? Towards the magnet. Okay. So magnetic field is up. So V and magnetic field is up. So that means the palm has to be pointing this way so that I can crawl it. So it goes towards the screen means towards the magnet. Yeah, The C makes perfect sense here. Now, okay, let's see if we can see that here. So if the force is acting in that direction, this thing should go in that direction, right? It should move in that direction. So let's see.
Through ground and then back home. Field pointing up, we expect a force inward. And sure enough, we get an inward force. Now, if I reverse the direction of the current, we expect an outward force. Oh, get this guy out of the way. And there you see it, floating there.
Okay, great. So now here I have basically written those things here. And here is one more exercise for you. Okay. So this cross means going into the page. Dot means coming out of the page. Here, this is on the page, going top on the top of the page. And this is going to the right. Okay, current is going to the right. Okay, so with that, I'll give you a minute to pull on this. Thirty more seconds. This is 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. So mostly D. That means it's coming out. So here, current is going this way to the right. So my right is that. So I need to start by, let's say, comfortably stretching my hand like that, right? And then now, should I be doing this? See, if I do that, then I can crawl up, but the magnetic field are not going up. Magnetic field are going on the side. So what I need to do is I need to turn this so that I can crawl in the direction of magnetic field. Means now the thumb is pointing up, means it's coming out from the screen. Okay. So that's why D is correct answer in this case. Okay, so that's the direction. Now, how about the value? So to find the value, we can start from what we know. So that is charge. And we know charge and current, they are related. Okay. So here, this is amount of the charge. This is velocity. And this is magnetic field. And this is angle between V and V. Okay. So now, what we can do is, okay, we want to introduce this length of the wire rather than velocity, because it's wire is not moving, it's the charge inside the wire is moving. And rather than finding the velocity of charge that's moving inside the wire, it's going to be easier if we write slightly differently. So let's write that velocity as a displacement over time interval. That's the definition of velocity. So now, so let's say if it goes through this distance of the wire, let's say this length of the wire, we can say, okay, that's the displacement it went through in time interval t. So that way the velocity is going to be displacement divided by time. And here, other way around, velocity is displacement divided by time. Okay. So we can say, okay, that displacement is line segment of the wire, length segment of the wire, and there is charge, and there is time interval, and charge divided by time interval, that's the definition of current, rate of flow of charge. Okay. So I can replace that by the current, and this by the length of this length segment of the wire. Okay. B is there, sine theta I just copied. So that's the right hand rule. In terms of vector, this is written as something like this. Since current is not a vector quantity, we say, okay, the displacement is a vector. So displacement is length of a wire in the direction of flow of current. Okay. So this is another way to write this. Just like another way to write this is QB cross B, cross product, right? So we're not going to be using this cross product much, but sometimes you may see it, and don't get afraid. It's basically, this is how it's supposed to be, but we are going one step simplification and writing like that. Oh, that's supposed to be this, not that one. Okay. So we know the value of the force in a wire, segment of wire that's carrying current I. And we also learn how to find direction of the force. So now here is one such example. So in this case, there are this is like a rectangular coil. And so that means it has 4 segments. Okay. So looks like if we were to say this is length and this is width, looks like we have 20 centimeter width and 30 centimeter length. So we can say length and width, or we can just use generic symbol that I have used in note. So let's say that is A and this is B. So A is 20. No, A is not 20, but 30 centimeter. And B is 20 centimeter, the way I denoted them, okay? And the current is exactly 1 ampere. And it goes clockwise, means circulating like that, okay? Find the magnetic force on each side of the loop if the magnetic field is that much Tesla. 2.5 Tesla. Okay. And to the left means the magnetic field is going something like that. So to find the force, it's asking for force on A and on B, right? And we know value of the force is I L B sine theta. Okay. So now for the segment, longer segment of wire, theta is what? See, the length is going this way and field is going that way, means the angle between them is 180 degree. And for this one over here, it is, see, the current is going this way and this is going that way, means the angle between them is 0 degree. So that means so these values of theta gives sine theta at 0. Sine 0 is 0, sine 180 is also 0. Okay, so that means they're not going to be force acting on that side. So 0 force acts on the longer segment. Now for the shorter segment or segment B, so the angle between them is 90 degree. Okay, angle between B and the current segment of the wire is basically 90 degree. The angle between them is 90 degree. Theta is 90 degree. So this gives us sine theta or sine 90 is 1. Okay, so that means F gonna be I L B, simply that. Okay, so we know all three values. So, and the value is going to be same on the, you know, like left side and the right side. Value going to be same. But the direction going to be opposite because in this segment of the wire, current is coming down. On this side, current is going up. Okay, so that means force going to be in opposite direction there. So the value is this, so you can plug in and find the values. So B here, make sure you convert that centimeter to meter. So that means 20 centimeter is 0.200 meters. So this is 3 sig fig problem. Okay. Oh. So everything is known. So the value is going to be same for both of them. Okay. Same value for left and right side of the coil. Or loop. I think it says loop, so let's say loop. Now direction on left side is what? And direction on the right side so I'll let you figure that out and we'll talk about it again after the break. Looks like it's a good time to take a break. Okay, so I am leaving here so that you know when you get chance you figure this out. I made a clicker question here. So left side means this here. So B is going this way and current is going that way. What direction is the force? Choice A, this dot means it's coming out of the screen, and cross means going into the screen, which is choice C. And then B means just going along the wire, so in the direction of current, and D is opposite of that. Okay, so these four choices. You have a minute for that. Thirty more seconds. Five, oh, 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see how did we do. So we have A and B, and there are some C, and correct answer is A in this case. So current is going towards you folks here in the camera, right? My 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 tablet is on the table. So current is going on the upside, means it's going like that. And the field is going this way to the right, in my case, towards my right hand. The hand, let's see. Yeah, to the left, not right. Okay. So my hand, so I need to crawl my finger towards the left. So that's why I need to start like this. So this is the direction of current. And then I need to crawl this to the left. So that's why I'm holding my hand like this, not like this. Okay, not like this, but like this. Why the palm pointing this way? So that I can crawl in the direction of field. So that means thumb is pointing up. Up means it's coming out of the screen. So that dot A, that makes sense. And now for the side B, or the right side, see, direction of B is same. Thing that changed is just the current. Now current is kind of coming towards me. So when we do that and then crawl, in that direction, what happens? The thumb goes down. So that means for that would be C, okay? So what that means? That means these forces, so force from here is coming out, or if I were to draw it, let's say something like that, okay? And over here, force is going in. They are in opposite direction, okay? But they have same value. So that's how it is acting. So that means net force is going to be 0, because since these two forces are equal and opposite, they're going to cancel, and there is already 0 force. So net force in this coil is 0. Okay. Now, although force is 0, torque may not be 0. So that's why we take that advantage of that idea that, torque is not 0 to make electric generator. So over here, this coil, so in my note, this is what I have is sketched, but looks like this is better here to show. So that's why I grabbed this one here. So this is like that. So in this case, looks like field is going opposite of what we had over there, right? So because of that, the force is coming out in this side and force is going that side. Now this coil is free to rotate here, okay? So because of that, this one makes the torque, and torque is, we know, force times lever arm. So lever arm in this case is going to be exactly half of the width of this wire, okay? So if we were to say B, it's going to be B over 2. If we were to say W, then it's going to be W over 2. Let's see, what did I write here? I think I wrote W based on this. So that's the torque on one side. See, here there is force 0, remember, okay? And then torque due to another one going to be, so that's going to be in clockwise direction because it's trying to rotate this way here, right? As indicated by this arrow over there. And we do the same thing for the other side. So the value of torque going to be same, and now it's trying to rotate this way, clockwise as well, okay? So that means the net torque going to be the sum of these torques, and since both of them are trying to rotate in the same direction, their sign going to be same, okay? So they add up. So that's why I am doubling, okay? Both of them have same value, means we can double that. So that's going to give us the value or the equation of the torque. So here is the length of this coil and width of the coil. Length and width, product of length and width is area. So because of that, what happens, even if it is not rectangular, let's say if it is circular coil, we can still use the same equation, okay? So it looks like these two gonna cancel, and combination of these two gonna give me area, okay? So that is the torque due to one coil. Oh, I haven't used the area yet. Looks like, okay, now that's that. So this is torque due to one turn of the loop or one loop, okay? But generally, when we are making generator, we put thousands of the coils there, okay? Thousands of them. So to get the total, we can just multiply that, okay, by n. So that's going to be that. And theta here now, see, there is A here and B. So this theta is angle between A and B. So area, how do we figure out area of a loop? Value, yes, of course we can figure that out. If it is circular, it's going to be pi r square. And if it is rectangular or square, then we multiply the side length and width. So that's the value. How about direction? See, here, this is a better equation actually. So the area here has a direction. That's interesting. So what's the direction of this area of this coil then when we write formula in terms of area? So it has to be the angle between A and B, okay? The theta is angle between A and B. A is area of the coil. So area of the coil gonna be normal to the coil itself, okay? Area of the coil gonna be normal to the coil itself. So what does that mean? So normal could be coming out or going in a loop or in an area, right? So for example, let's say, let me briefly share my screen so that you can see it. So I have this thing here, let's say. So this is the area. We know how to find the area of this one there, right? But how about direction? So what I'm saying is direction gonna be this way, coming towards you, towards the camera, or opposite, okay? So now what determines whether it's going to be this way or that way? So for that, we need to look at which direction current is flowing in the loop. Okay. So for example, if current is flowing in this loop, something like this, so seen from that side, that's going to be clockwise, I think. So is my finger going clockwise right now for you folks? See, it's going this way and that way, and that way. Is that clockwise? So anyway, what you want to do is finger here, line up like that, okay, in the direction of flow of current, and I'm gonna point either this way. So in this case, if current is going that way, then it's gonna point that way. If current was going other way, this way, then the thumb gonna point towards me, okay? So that's what determines the direction of the so I knocked down my microphone. Okay, so that's what basically gives us the direction of the area. Okay, so the angle gonna be the angle between the normal to the area and the magnetic field. Okay, so when magnetic field is perpendicular to the plane, then what happens? Normal and magnetic field, they are in same direction, so theta is 0. So angle 0 in that case means torque gonna be 0. But when magnetic field is parallel to the plane means now the angle between area and B is 90 degree. That gives us maximum torque. So the torque varies when this one rotates, okay? So let me share this again. So what happens is the value of torque changes with the angle. So it is 0 to maximum value. So maximum value going to be this much, okay? So when sine theta is 1. And when is it 1? When theta is 90 degree and theta is angle between normal and B, okay? Normal to the plane B. So over here, the plane gonna have normal either this way coming out or going that way. And when we have field like that, and let's say if the normal is something like that, so that's going to be the angle between A and B, okay? So when this plane is flat, like in a magnetic field, so in that case, normal going to be 90 degree from the field, okay? So for example, let's say we have a coil like this and field like that. The normal going to be coming out here, let's say something like that. So the angle between this line and the vertical line that's coming out from here going to be 90 degrees. So theta going to be 90 degree. And that's where this becomes maximum. And I think there was a question on the, the practice and the pre-class assignment. And there was some problem on that question. I fixed it, but if you open your test and then left it there to do the second or third attempt, what happens in that case, my correction doesn't go there, okay? But if you open the test after I corrected, then you should have seen the, correct form of question. Otherwise, you may have received, that with the same choice for two of them, same choice, I think, something like that, okay? So some of you already emailed me And if you saw the same choices and because of that you did not get credit, write me email and I'll give you credit for that, okay? But if you saw both perpendicular and parallel option, then it was the corrected version you opened, okay? So for example, we have something like this. In this case, it says, okay, theta is 10.9. So theta is given. So everything is given in this case. So what is maximum torque? Torque is maximum when theta is 90 degree, because we have equation sine theta, and sine is maximum. Maximum value of sine is 1. So when does the sine becomes 1? When theta is 90 degree. So torque maximum is basically comes from here, this NIAB when I was a student, I kind of wrote something like this, BINA, and it used to be the name of person, Bina, okay? So that's how I remember. We did not get formula sheet in our test. We had to memorize all the formula, okay? So anyway, so that's that. So that's what we want to calculate. So do we know everything? I think so. Theta is 150 turns. And then it's a square loop. So that means length and width same. So 18 centimeter means 0.180 meters. So area gonna be L squared because it is a square. And then current is 50.0 ampere, and B is 1.60 Tesla. So that means T max is product of all these number, and unit of torque is Newton times meter. Remember, torque is lever arm times force, so we can just multiply that. So now for B, you do the same thing, but in this case, theta is 10.9 degree given. So that means now torque not going to be maximum. It's going to be different value because the angle is not 90 degree. So it's going to be NIAB sine theta and theta. So everything you plug in, and this going to be less than this one. Okay. So this is basically same as this number. So if you put that without, let's say, rounding, that should be fine. Okay. All you have to do is just multiply that by sine of 10. And this number is not that big. I think it's something like 0.1 or something like that, but I don't know exactly. So anyway, so that's how they torque. So now what we can do is we can make use of this knowledge and torque and put that in a magnetic field so that it just turns. Okay. So here you have to pass the current. And now this thing is spinning. So now that's how the motor on the blender, fan, everything that spins with electricity, you know. So you supply the electricity and then it spins, right? So that kind of motor is designed based on this. So now imagine now how many things that uses motor, right? And how useful it is, that knowledge. So how much it had helped for us to, like let's say, for example, blender, right? So blender has this motor there, something like that. So they have actual coil looks something like this, okay? So otherwise, see here what happens, the torque becomes 0 to maximum if you have just one flat coil. So because of that, they kind of makes this several coil going in different angle. That way, what happens? It keeps spinning rather than spinning and stopping like you see over here with just one coil in one direction versus over here several coil in several direction. Okay. And the same thing. So for example, when we are using ammeter to measure current or voltage, basically we are passing current through the coil, and there is a magnet. So what happens? The current produces torque and there is a needle attached to that. So depending on how much it turns, what happens? It deflects, and that's how you get the reading from the meters. Okay, so that's about the torque in the coil. Now, let's talk about force between two wires. So we learned that when we put a wire in a magnetic field, it experiences force. And we also learned that when current is flowing through a wire, it produces a magnetic field. So for example, here, there is this current flowing through this wire. That's what I have drawn here. Let's say at a distance r, what's going to be the magnetic field? So we know direction of magnetic field can be given something like this. So that means our thumb is pointing this way, means the fingers are coming this way, fingertip means the field is coming this way and field is going that way. So on this side of the wire, everywhere there is field going into, okay? And in this side, what happens? The field lines, they are coming out. So now this current in this wire means there is field on this side, right? So now let's just draw the field somewhere at this point here, okay, where we want to put the second wire. So there is this field. See here, current is I1 here. So field is B1 due to that current here. So since we are looking at this side of the wire, everywhere on this side, the field are going into the phase using this right-hand rule. So here I'm interested in this area here, this region. So that's where I drew those cross. Okay. So now what is the value of this magnetic field? We figure out the direction at this point. What's the value of magnetic field at this point? So that's where we use this equation here. Okay. So Ampere's law we learned, right? So it is the current in this wire and distance from the current carrying wire is R. Okay. It's like a radius of that circular field. Okay. So now we know this field. And we just learned that if we have field and if we have a wire that's carrying current, it's going to experience force. Did we learn that? And we find direction. So that force is given by ILB, an angle being 90 degree. I can just say, okay, that's ILB is the force value. How about direction? Just like we did exercise on that coil, right? The same idea here. So that's how we want to find the force on the wire. Okay, so there is the second wire. Now the second wire that has current I2 is sitting on a magnetic field produced by this first wire. And remember, it's like, so you may be thinking, okay, how about the field due to this one? So what happens is like the field produced by I2 does not affect I2 itself. Field produced by I2 gonna affect the I1, but not itself. Same thing goes with the field produced by I1. Field produced by I1, which I am denoting by B1, affects the I2, but not itself I1, okay? So that's what I'm showing here. So understanding this step by step is important to understand, how these forces are acting. So now let's focus on this field and then this wire that has current I2, okay? So force on I2 due to this field B1, using this equation that I2 current times length of this wire, but field coming from this wire, so I can write that. And then we just use this, we can write field in terms of the current in that wire. So that means we can write something like this, okay? So it has current from both of these wires now, but the length of the wire is just second wire, okay? So now let's figure out direction of F1, or the force on this due to current I1, okay, or field B1, I should say, rather than current I1. So force on wire number 2 due to field B1. So now we start by lining up our forefinger in the direction of field, means flat hand, but see, it's a flat like this, horizontal, because my paper is sitting on the table, okay? If you are looking at the screen, which is vertical, you can do something like that, okay? Now field is going into, so you need to, crawl your finger into that. So that's the direction of force. So this force is pointing towards current number I1, okay? So force is pointing to the current number I1. So that means the force here is acting this way. That is F1, okay? So now to find force on this one, we need to use the field due to this current. So that means that B2 gonna be just same equation as this, but now I1 is replaced by I2. And then now force, we do the same thing, but this time, what's gonna happen here is this length of the wire gonna be not L2, but L1, okay? Using the same technique here. So this I1 and I2 is still gonna be there, but now we have L1. Here we had L2, okay? Because that's the length of the wire that's sitting on the field from current I1, and that field we denoted by B1, and same thing goes with the B2. And field at B2, see, this is wire. So we are looking at this side. So on this side, these fingertips are coming out from this side of this wire, okay? So field are dotted field on this side of the wire and cross on that side of the wire. I'm just talking about field due to current I2, and I'm denoting that field by B2, okay? And the direction of that field using this right hand rule is that these fingers are coming out, means it's pointing up. So that means the current I1 is sitting on this field B2, which is pointing out or coming out from the screen or the paper. Okay. So now how do I find the force? So in this case, we crawl our finger towards the screen. But in this case, we need to crawl our finger away from the screen or towards us. Okay. So again, we start with flat palm here, but this time it's not pointing down, but pointing up because fields are coming up. So that means we want to crawl these fingers up. Okay. So now thumb is pointing towards the wire number 2 or current number 2. So that means the force F2 is pointing that way. If they have same length, the value of the force is going to be same. Okay. If these two wires have same length, remember, everything else is same. So that means only the length is different. So if we have wires that have same length, then the forces, value of the force also going to be same. It's like equal and opposite. One wire is trying to pull another wire, and the another wire is pulling the first wire, like action and reaction force there. Okay, and that is the case when these current are flowing in the same direction. But if we were to reverse one of the direction of the current, then rather than attraction, there are going to be repulsion. So I guess, you know, so let's say there is one something like this, another something like this, I1, I2. Now, and by the way, all these steps I talked about, they are written in a stepwise in the note. So let's say if you have something like this, so now what's going to be the field here, B1? What is going to be the direction? What's going to be the field over there? What's the direction, right, due to that? So you figure that out. And then using right-hand rule, you figure out the direction of force. And see if you can verify that they're going to be repulsive. Okay? So that's for you. And there is more for you here. So now there is one current carrying wire. So that means it's going to produce magnetic field. So that means this loop here is sitting on a magnetic field produced by this. So that means this loop may experience force. Okay. So now the question is, what is the direction of net force on the rectangular loop due to field from long straight wire, means this one, and choices are here. Okay. So you have 2 minutes. Go ahead, figure out. First, you need to find field due to this. Find field due to I on this side, on this side. So that's the field this thing is sitting on. 30 more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Let's see what we got. Oh, we got all of them. It's kind of starts from A and kind of decreases. So find the field due to this current. So if I were to grab this wire by pointing finger in the direction of current, my fingers goes into this side and comes from this side. Let me just put dots. So that means everywhere on this side, field is coming out. So the one that's closer to the wire, that's going to be stronger. And as we move further out, see, R is in denominator of that equation. B is mu naught I over 2 pi R. See, the R is in denominator, means as we move further and further, the value of the field decreases, but the direction is still same everywhere. So now it's like a one wire in a magnetic field. So now we can use that right-hand rule by lining up our fingers in the direction of current. And since the field is coming out, I want to flip my palm up so that I can crawl my fingers up. So now my thumb is pointing this way. So over here, looks like the force is going to be pointing this way. Okay. And now this, what's the difference? See the dots? The field is in same direction, but current is now reversed, means this force is going to be pointing in that direction. So every point, this force is going to be pointing equal and opposite. So net force due to this side and that side going to be 0. How about this side and that side? So let's figure that out. Okay. Field is still coming up, but now the fingers has to be pointing to the right, but the palm has to be still pointing up so that we can crawl up, right? So now the finger is coming towards me, so that means this is the direction of force here. Okay, and field is stronger over here compared to field at this point, but the direction of field is still same, so that means the force gonna be in that direction there. Okay, but this force here is stronger because field is stronger there and this force is weaker. So that means net force in what direction then? So this is stronger, this is weaker. So let's say if this is positive 10, that means this is going to be, let's say, negative 5. So total going to be positive 5, means pointing in that direction. Okay, so it looks like C is correct answer in this case, folks. So yes, it is a little longer. So all the knowledge we learn that goes into this question. So it's kind of tough question, but if you master this, you're going to be champion on finding directions. You know what direction the field is and what direction the force is, and so on. Okay. So it is exactly 50. So it looks like it's time for us to say goodbye for this week, and I'll see you next week.
I have a quick question.
Okay.
Like you said that the direction of current creates field, but I know that the electrons flow is opposite of current. And I was thinking where electrons flow, the field flows. So I was like, why is current and field the same direction and it's not with electrons, if that makes sense?
So current is flow of electron, but when we show a current like this, that means we are assuming it's the positive charge that's moving, okay? So yes, so but see here the charges are moving, and the charge is moving creates field at this point, at this point, at this point, everywhere, okay? Since the coil is over here, we are interested in field in this portion. See, the wire is not moving, just the current is moving. So wire is there. So this wire is producing the field. So that's why field is not moving. Okay.
Okay.
And field is related to the distance from the wire. There was a question on the Zoom. So it depends on the distance. And farther we go from this current carrying wire, it becomes weaker because it's inversely related to distance.
That makes sense. Thank you.